Hi everyone, welcome to our webinar today. The topic of today's webinar is Evaluating Technology Impacts on the Distribution System, PNNL's GridLAB-D simulation tool. This webinar is presented by Clean Energy States Alliance as part of CISA's multi-state initiative to develop solar in locations that provide benefits to the grid. Our host for today's webinar is Nate Hausman. Nate is a project director at CISA. We also have an excellent guest speaker on the line with us. Before I pass it over to them, I'd like just to go over some quick housekeeping notes. All of our attendees are in listen-only mode. You have a couple of options to join the audio portion of the webinar. You can either call in via telephone or you can connect via your computer's mic and speakers. If you'd like to minimize the webinar console so that you can view the webinar slides full screen, click on the little orange arrow that you see circled here. You can also use that orange arrow to expand the webinar console. Following our webinar presentation, we are saving about 15 minutes for a Q&A with the audience. We ask that you please submit your questions by typing them into the questions box on your webinar console and hitting send. We will get to as many questions as we can, but have a lot of people registered for this webinar today, which means that we'll probably get a lot of questions and we might not get to yours. To make sure that we get to as many as possible, please type them in when you think of them. Don't wait until the very end. Finally, this webinar is being recorded. We will post a recording of it on our website, www.cisa.org/webinars, and we will also send you a follow-up email within about 48 hours with a link to the webinar slides and recording. Now I'd like to pass it over to our host for today's webinar, Nate. As I said earlier, Nate is a project director at CISA, and he will be introducing our webinar topic and today's guest speakers. Nate?
Thank you, Mari. Sure enough, as Mari said, my name is Nate Hausman, and I am indeed a project director at the Clean Energy States Alliance. In case you're not familiar with the Clean Energy States Alliance, or CISA, we are a national nonprofit network of public agencies and organizations, and we work together to advance clean energy. You can see our members on this slide. It's mostly state agencies. And as Mari said, this webinar is being conducted as part of our multi-state initiative to develop solar in locations that provide benefits to the grid. You can move to the next slide. Yeah, under this project, CISA, we're working with 5 states and the District of Columbia to identify locations for solar and other distributed energy resources that provide benefit to the grid. You can see the states we're working with on this slide. In Connecticut, it's the Connecticut Green Bank. In DC, it's the Office of the People's Council. In New Hampshire, it's the Sustainable Energy Division of the Public Utility Commission. In Rhode Island, it's the Office of Energy Resources. In Washington, it's the State Energy Office, housed in the Department of Commerce, and in Wisconsin, it's the Office of Energy Innovation. The project is part of the Solar Energy Innovation Network, which is a collaborative research effort to explore new ways solar energy can improve the affordability, reliability, and resilience of the nation's electric grid. NREL is operating the Solar Energy Innovation Network, and they're doing it with funding from the Department of Energy's Solar Energy Technologies Office. Today's webinar is on the PNNL, Pacific Northwest National Laboratory tool called GridLABD. GridLABD is a distribution technology simulation software tool. It's been used to evaluate technologies like demand response, solar PV, smart inverter control strategies. And with us to talk about it is Frank Tuffner. So let me introduce Frank. Frank is a staff research engineer with the Pacific Northwest National Laboratory and one of the contributors to the openly available U.S. Department of Energy Office of Electricity funded GridLABD distribution modeling software. Since joining the lab in 2008, his research has primarily focused on transmission level stability and the modeling and evaluation of distribution level systems and technology. This research has included small signal stability, time synchronized measurement device use, modeling and evaluating distribution automation technologies, the impact and use of distributed energy resources like electric vehicles and PV arrays, and microgrids for resiliency. So with that, let me pass it over to you, Frank. The platform's yours.
All right. Thank you for the introduction. Get my presentation up here. There it goes. So as mentioned in the introduction, today we're going to be talking about the GridLABD simulation tool that was developed primarily at the Pacific Northwest National Lab. It has components that have been contributed by universities and other Department of Energy national labs. So if you're not familiar with the National Laboratory System, the Department of Energy operates 17 national labs scattered throughout the country. A lot of them have kind of different areas of expertise or different specialties. Pacific Northwest National Lab is located up in Washington State. Our main campus is in Richland, Washington, in the southeast corner of the state. We also have some satellite offices in Sequim, Washington, which focuses a lot on kind of coastal sciences and any type of ocean-related research. We have a Seattle office, which is where I'm located, which does a little bit of that coastal research. It's also kind of more of a direct satellite office for people who are engaged with some of the local utilities like Puget Sound Energy, Seattle City Light, just being closer to those so when we do the interactions, we don't have to cross the strait to do so. As mentioned, though, a lot of these other labs have made contributions to GridLABD over the years. In particular, the National Renewable Energy Laboratory has contributed some work on the co-simulation and the photovoltaic capabilities that I'll describe later. Sandia and Los Alamos have been very involved in the microgrids research. Oak Ridge has helped out in some of the economic modeling, as well as some of the protection and the microgrid modeling. And then Berkeley Lab has been very much involved in some of the economic evaluations as well. Just a quick overview on PNNL, standard slide that has to be in every presentation. The lab itself is about 4,500 employees. About 2,500 of those are the actual research engineers or research scientists. The rest of them are support staff and kind of operations. PNNL has specialties in kind of a lot of different areas. Power systems and kind of power grid analysis is one of our key areas, which is where I'm involved. PNNL also does quite a bit of work with coastal sciences, a lot of fundamental chemistry, looking at kind of how things like batteries can be improved, as well as a lot of kind of other fundamental sciences, looking at biology, impacts of kind of different technologies on people and animals, very wide range of research topics, all under the Department of Energy or under the Office of Science. So getting into what the presentation is actually about, GridLABD, what it was developed for was primarily a way to evaluate the quote-unquote smart grid technologies. When GridLABD first came to be a little bit over 10 years ago, there weren't really any good simulation platforms that would allow you to look at kind of multi-domain problems. In particular, if you wanted to look at something like demand response, a lot of times you would either have a power system simulator, maybe a separate market simulator, and if you were lucky, maybe you would tie those together somehow or get some type of integrated solution out of them. However, as we started looking into a lot of the concepts like demand response or retail markets or kind of distribution markets on the system to influence the behavior, we started examining or noticing that there were a lot of kind of secondary impacts that those simulators were not capturing. So GridLABD was created as a way to unify all those different aspects of distribution systems so you can model them in whatever level of detail you require and get kind of the impacts of those technologies or the impacts of those approaches captured hopefully before you've actually deployed a system or before you've gone too far down the evaluation process. That way, if there's any caveats or if there's any impediments to getting the technology deployed, you find out about them early on in the process where you still have plenty of time to either mitigate or change your approach. Just some key highlights on GridLABD itself. As I mentioned, it is mostly for smart grid oriented projects. Basically a lot of your multi-domain where you have things like a building model interacting with a distribution system electricity model, maybe interacting with like some type of pricing scheme or retail market. And if you really want to go into it, if there's any like communication infrastructure you want to overlay as well. And that's something I'll get into later in the presentation. GridLABD is very flexible in terms of the timescales you look at. It can do milliseconds up to years. And where that's really helpful is if you're doing something like microgrid stability, you'll be really down in the details looking at sub-second type behaviors on your system, but you might be more interested in how that behaves over the long range, or if you layer like a demand response scheme on top of that, what is your annual energy consumption? How does that get influenced? Do your losses go up for the year? So you can turn around and evaluate that in terms of what kind of capital it might cost, or how it's going to affect your revenue stream, what kind of long-term impacts there might be on the system. So it has a very wide range of time periods it can simulate to reflect the different types of analyses. One of the key things I want to point out here, and it was mentioned in the introduction, GridLABD is openly available and it is open source. All of the source code is actually up on GitHub. You can download it, modify it, and we encourage people to contribute changes back. So if you're kind of on the more technical side of the evaluation and you implement a new feature and you want to make it publicly available to everybody else, we highly encourage people to contribute back to the source code. The particular license we use is what's known as a BSD style license. I think it's Berkeley Software Development. I can't remember what the acronym stands for. This is a very commercial friendly license. It basically allows any commercial vendors to develop their own capabilities in GridLABD or build something on top of GridLABD and then still sell it. And you don't have to worry about the contamination of the GPL license, where you have to make all of your stuff open source as well. With this style license, you could technically go download GridLABD, compile it, and sell it tomorrow, and that would be perfectly okay. There would be questions on why you're selling an open source software that people can get for free, but that's somebody else's issue. So if we look at kind of the 5 key areas where we've highlighted that GridLABD is using the open source capability and people have contributed to do the different types of analysis, it's really been a confluence of kind of the power flow. So that's a lot of your standard distribution electrical system, any control systems on top of that. So that could be any distribution automation. That might be some manual seasonal operations that utility crews are doing, or even something that's influenced from outside, like how a wind turbine might be influenced by the weather or something similar to that. Retail markets, if there's any type of transmission market that influences your system, you can factor that in. Where this has really been used has been more of if you want to overlay any type of kind of double auction or real-time pricing scheme on top of a distribution system, especially for concepts like demand response or peak reduction. Electromechanical dynamics, this is primarily down in that milliseconds range I was talking about. We've used this mostly for things like microgrid analysis and modeling kind of more complex devices and seeing how concepts like inrush, if you're familiar with that, might influence your system. So allow you to go really far down into the detail if you desire to do so. And then one of the big highlights of GridLABD is the end-use load behavior in the tens of thousands of buildings or devices. GridLABD is an agent-based simulator. So what that means is each individual kind of model in there has its own set of characteristics and its own set of parameters, its own set of state variables, own set of kind of characteristics that it is keeping track of. It interfaces with other objects, but it is primarily concerned with itself. And where that is really useful is in things like demand response. You can get some unexpected behaviors. I hesitate to call them emergent behavior because I know that has some loaded connotations in terms of artificial intelligence and everything. But you get some unexpected kind of aggregate behaviors that if you just used an equivalent model, you wouldn't see. I'll get into this in one of the examples later, but a classic example is if you have demand response on your system, you might do like a critical peak pricing or a curtailment event. Now you've synchronized all of your loads. So everybody's air conditioner turned off at the same time. All of them want to turn on. And when you release that price, everybody will turn on at the same time. And you may have actually made your problem worse. Without doing those individual loads, that behavior may not be captured. And you might not realize that by deploying the demand response scheme just as a pure peak curtailment, you might have some secondary effects that you have to manage as well. The beauty of GridLABD is while it can go to that level of detail, you don't necessarily have to. You can pick the level of detail you want to model your system. You could do it as a pure power systems analysis and don't have any end-use load details, or go all the way down to the individual toaster in your house and figuring out when you're actually cooking toast. I would question why you need that level of detail for certain types of studies, but you have the full capability to do so. So here's just kind of some more high-level points on it. The The big thing with GridLABD that's not as unique anymore, but really was when it was first conceived, is doing time series analysis. A lot of your traditional distribution system evaluation tools at the time, they only did snapshots. They would do something like the peak load day, or maybe the hottest day of the year, or something like that. They wouldn't really capture any of the time evolution of the system, and that became very important when we started looking into things like demand response and using load as a resource, which I'll get into here in a little bit. That time varying behavior becomes very important because, like that demand response example earlier, if you're doing it only from a peak load scenario, you might accomplish the goal of the study, but then there's a secondary effect after you've released your curtailing event that actually causes the distribution system to be overloaded. So without capturing that time behavior, you may be missing problems that are coming out of a result of the technology being deployed or of the particular operational procedure that you're looking at. Some typical use cases, and we'll go into some of these in a little bit more detail. The interconnection of distributed generation and storage, how deploying things like photovoltaic or local energy or community level energy storage might influence your distribution system and what kind of benefits it might have. New and innovative retail market structures for distribution system operators. If you wanted to have basically a retail market overlaid and have end users or end use appliances operating in real time on that, bidding in their desired demand, and then reconciling the market, figuring out how much you're willing to pay for electricity and adjusting your demand accordingly. Very closely related, the evaluation of demand response and energy efficiency, different types of studies to see if something like a demand response program would help you defer a capital investment or something similar to that. Volver Optimization, conservation voltage reduction, deploying that technology, seeing what kind of benefits you can get. The last two are kind of more of our more recent research ideas and kind of research evaluations. One of them is on sectionalizing, reconfiguration, automation, and restoration. This is either during normal operation or during like a disaster scenario, if there's like a tornado that goes through the system or if there's a wildfire. How do you change the way that system is physically connected using some automated or some manual switching devices in order to get around the damaged section? Basically, so if there is an outage, how can you get power back to the maximum number of customers in the most timely fashion? And then microgrids and resiliency, once again, for kind of a disaster scenario, if you have any distributed energy resources, especially capable photovoltaic or like backup diesel generators, how can you use those to keep your critical loads online through a disaster or while you wait for the main power system to come back? So over the years, I mentioned that there have been quite a few national labs and universities that have contributed to GridLABD. This is just kind of a highlighting slide of several of those. Basically, a lot of the national labs are down here in the lower left-hand corner, a lot of universities over on the right, and then some commercial entities on the top here. And I'll go into some of these in a little more depth here shortly, just with some use cases we have. So one of the things we really like to promote with GridLABD is that it is working with industry. As a national lab, our place in kind of the research area is a bit of a halfway point between industry and academia. So academia will typically develop kind of the new algorithms or the new approaches, and then the national lab is there to kind of help transition that or evaluate if that can actually help the utility or the grid as a whole. And we've had a lot of projects along those lines where we've taken either a high-level concept or an academic concept and then helped demonstrate it to utilities or help transition it to something they can use on a daily basis. A couple of those are here. One of them is the Open Modeling Framework developed with the National Rural Electrification Cooperative Association and CRN. This is basically an open source web-based cost-benefit tool. You can go to the website. You can either use a sample distribution system they have already uploaded, or if your data is in the right format, you can upload it to their web server and do a lot of different evaluations of if I deploy conservation voltage reduction, or if I want to do this type of upgrade to my system, what would the impacts be on that? And that web interface is actually running GridLABD under the hood to do a lot of the actual distribution system and simulation and provide the results that it's analyzing and providing the feedback to the user via the web interface. Very similar to that, we've also had some work with industry in terms of the commercial distribution analysis project or products. MillSoft, with their power system simulator, has built in a GridLABD translator for their utility users. And where that's really handy is if you have an existing model in something like MillSoft, but there's a newer technology that you want to evaluate or see what kind of impacts it would have on your system, that technology may not be implemented in those commercial software, or it may not even be something they plan to implement anytime soon. So the ability to export into GridLABD and then run it on kind of the research side lets you look into some technologies that maybe you want to be on the leading edge of a particular deployment, or you think that a new technology that's just coming to age might solve some of your problems. You don't have to wait for the commercial sector to catch up. You can transition it over to the open source GridLABD, evaluate it, and get your answer a lot sooner. Another one, which I'll actually go into a lot more detail later on, is a project we had with Grid Unity. They were Cato Energy at the time, and Southern California Edison. They wanted to design or create a photovoltaic or distributed generation integration tool, basically find a way of kind of seeing where PV might deploy and quickly evaluating if that would cause any issues on a particular power system. And then if there are issues, what kind of mitigation strategies could be done there? Would there be new technologies they would deploy? Could they maybe move where it's connected slightly? Things of that nature. And the idea was to make that very user-friendly, give it a nice front end, and let utilities, and I believe even end users, have access to it to quickly look and see if photovoltaic was possible where they were and what kind of impacts or changes they might have to do in order to integrate with Southern California Edison's system. So throughout much of the analysis or the examples I'll go through here, obviously for a distribution system, you need to have a model of that. And some of the analyses and a lot of kind of the higher level concepts are typically done on some generalized test models. These include, there's a bunch of feeders done by the IEEE Distribution Feeder Working Group. These are openly available, just kind of typically lower order models. They were meant to test like power system solvers or test a particular feature on a distribution system, but they are a good basis for doing some very simple studies. Another one is the taxonomy of prototypical feeders. This will be heavily used in some of my later examples. What this is there was a Department of Energy Modern Grid Initiative effort about 10 years ago, and it took all of the kind of distribution systems in the continental US and did a statistical average on those and came up with a representative set of feeder models that you could use to evaluate technologies. These are systems that are based off of actual feeders, but they're not actual feeders, so there's no data sensitivity issues, there's no proprietary information in them, but you can turn around and use those in GridLABD to evaluate something like demand response for your particular climate region and get the information you need without having to actually load in your model, either because there's some sensitivities associated with it or because you may not actually have the model. Then a more recent one we have is what we call the Smart City model, and there's just kind of a one-line diagram of it over here on the right. What this one does is it creates a much larger multi-feeder model in order to evaluate some kind of larger impact distribution system technologies. This actually has multiple of those prototypical feeders attached to it. That's what the different colors are here. The other thing it has is a meshed urban core. So if you're in a larger city, a lot of your downtown areas operate their power system slightly different in order to increase reliability. That way, if there's either an outage from one transmission line coming into the city, or if there's like a transformer that gets hit by a delivery truck, all of your buildings in the downtown don't go dark. They have some redundancy built into them. If available, it's always nice to also do utility-specific test models. I mentioned the open modeling framework, and that has the ability to import certain types of models. We also have some scripts if anybody wanted to evaluate a technology and they have a SIME or a synergy model. the ability to extract those and put those into GridLABD format so you can run the different types of analysis. Worst case scenario, although it's never a preferred option, there is the one-line diagram manual extraction. That would basically be where you take a picture very similar to what's on the right, and you would manually enter and create everything on that picture. Definitely not the ideal way to go, but if you need a model and you don't have any other alternatives, that's the best way to go. Something that like I said, I'll get into here a little bit later, those prototypical feeders especially were divided up by climate regions in the United States. And what we created for those, which is also freely available, or openly available, is the population script. And what this does is it allows you to take the base power system model and populate it with a representative load base. So different types of houses for different climate regions, get some end use behaviors. So when do people usually run like their showers or their dishwashers in that particular climate region, since that can impact your power system. What type of appliances do they have, especially from an electricity perspective? If natural gas is prevalent in that region, the electrical impacts would be very different from somewhere where electric water heating and electric house heating is the more dominant source there. And then, of course, if you want to add in things like distributed generation, it allows you to basically choose the level you want to deploy and then randomly distributes it throughout the feeder so you can evaluate different impacts on your distribution system, like if deploying solar will cause you any voltage issues or overload any lines, or if it might mitigate some issues, and just generally give you some flexibility to try out different scenarios. So getting into some of the actual analysis, one of the more prominent examples that has used GridLABD is as part of the American Recovery and Reinvestment Act 7, 8, 9, or 10 years ago. I can't remember how long ago it was. Part of that included the Smart Grid Investment Grant projects, where there were grants provided to utilities and organizations to basically deploy some newer technologies or evaluate them and see how they might improve their system. The Department of Energy, via a request from the Office of Management and Budget, sent a request to PNNL to evaluate these technologies and see from a technological perspective or a technical perspective what impacts they would have on actual distribution systems. So we weren't looking at the economics directly, and we weren't looking at any of the other goals of the American Recovery and Reinvestment Act, like job creation. This was purely, if these technologies were deployed, what kind of benefits would the power system or the utilities see? So on the slide, there's a bunch of different technologies that were evaluated. The results are in the kind of bronze over on the right-hand side. You can see there were a variety of different smart grid technologies that were being looked at for the SGIG program. Volver Optimization, reclosers for reliability, distribution and outage management systems, or DMS, fault detection, identification, restoration, that's also known as FLISR, different types of energy storage, in particular thermal energy storage for commercial buildings. This is a lot of kind of like your ice bears that typically go on the roof and supplement HVAC systems, as well as residential photovoltaic, if there were any benefits or issues with that. Where this became very useful is kind of this plot down here in the lower right of seeing what the cost-benefit analysis is of the different technologies. This particular plot is actually for conservation voltage reduction or Volver optimization, and is showing kind of what is the benefit for the number of feeders in the United States you deploy it to. And you can see there's kind of that quick rise up to about 50%, but then beyond 50%, deploying it on additional feeders, you're still getting some gain, but it's not very significant. And if you're familiar with the Volver optimization scheme, that makes sense that certain feeders just are not going to benefit, or they may actually behave poorly with that technology. But being able to apply that to a national scale was very useful, not only for the Department of Energy kind of reporting back to the Office of Management and Budget, but also to utilities, so they could look at this and say, you know, something like Volver optimization or CVR, maybe we can use this to determine which feeders we want to deploy it on and save ourselves some money. Whereas if we deployed it on all of our feeders, there may not be as much benefit as we expect. Another project we did was looking at scalable demand response with dynamic pricing, and this was in collaboration with the NRACA. What this overall project was really looking at is the utility of interest. They had a very good partnership with another utility that had some generation assets, and they were trying to leverage their two strengths in order to avoid doing a capital construction cost or a construction project of a new distribution feeder or a new substation. They wanted to see if there were some quote unquote non-wire solutions like energy efficiency or demand response to help either push out that capital investment or maybe eliminate it completely. And what this was doing is, if you're not familiar with kind of time of use or critical peak pricing or real-time pricing rates, it's sending out a pricing signal to your end-use devices or your individual homes and consumers, and either the user or the appliances themselves have some intelligence built in that say, you know, this is the level this is the cost of electricity I'm willing to pay, this is how much I want, and submitting that back up to the system and saying, I want, 5 kilowatt hours at 3 cents per kilowatt hour. And the market will reconcile all of that with the price of the generation and the availability, and then kind of send back a pricing signal or some type of incentive signal. So maybe if you wanted to dry your clothes at 5 o'clock, that might not be the best time. But if you wait until 7 o'clock, it would be much cheaper. Probably not too inconvenient for you, but it helps the power system out and helps the utility defer that cost till further down the line. A couple things I wanted to highlight on this slide especially were the time series behavior of GridLABD is especially important. Is you see the traditional critical peak pricing program, you get this rebound effect. And what that is that synchronization effect that I mentioned at the beginning of the slides. So if you do your demand response call about 2 o'clock in the afternoon here, you'll get the load to go down because a lot of your end uses will turn off or the price is too high, so they'll defer. When you release that price around 6 o'clock after you've passed what you think is your peak period, everything that has been turned off or has been waiting suddenly wants to turn right on, and all of your loads that used to be kind of distributed through time are now all turning on at the exact same instance. So you get this rebound effect where in the process of reducing your peak, you may actually make a bigger peak and cause all sorts of other problems on your system. So what this looked at was doing what we call the staggering critical peak pricing start time. So where not everybody is on the same pricing signal, or when you release it, not everybody gets released at the same time. And what that does is that allows there still to be some time diversity in how the loads behave and keep that peak below the critical peak you're trying to reduce. If you weren't using something that captured kind of the individual end use behavior or the time series simulation capabilities, you would miss this, and you might deploy a demand response based off of this red dot here and say everything will be great. And then once you get it deployed, find out your system actually gets significantly more overloaded than it was, and now you have to deal with that problem. So this is a very good highlight of where kind of the capabilities of GridLABD are very useful for evaluating some of your smart grid technologies that may not lend themselves to traditional analysis. Another example that GridLABD has been used for is a technology developed at PNNL called the GridFriendly Appliance Controller. This is basically an under-frequency load shed device. What that means is when the power system is heavily overloaded, the 60 hertz grid frequency actually moves around a bit. It'll go low. And that's a signal that you can detect at your end-use device and tell it to turn off to help kind of prevent the grid from going down. So if the power system is overloaded, this little device can basically turn off non-essential appliances, something like your dryer, maybe the heating coils disable, or if your refrigerator is doing a defrost cycle, maybe turning that off for a moment, basically alleviating the load on the grid so the transmission side can recover, get back up to a stable operating point, and prevent either a blackout or a brownout, all via the load. And where this really got in, the initial grid-friendly appliance was just kind of doing that under-frequency load shed, but it enabled starting looking at kind of loads as a resource. So if you're familiar with power system operations, a lot of the traditional way to operate the balancing and the frequency is to do everything on the transmission side and on the generation side. So if there's too much load on the system or too much demand, you have to bring some more generation online. Maybe that's, a dirtier kind of fossil fuel source. Maybe it's something that you have to keep idle and it costs you money while it's running, or maybe you have to buy that from a neighboring utility. The capabilities of GridLABD allow people to go in and look at that from the other side of the other side of the equation of what if you could use the loads as a way to mitigate that increased demand. So if the power system is getting overloaded, can you send a signal out and actually tell, say, your toaster or your dryer to not use as much energy and actually help the grid remain stable and keep operating rather than there being a blackout or the electricity prices going through the roof. And this eventually transitioned into what's called the transactive control for ancillary services. This was part of the Pacific Northwest Smart Grid demonstration. This was looking at using kind of a transactive signal, so that would traditionally be something like price, but some type of incentive to see if you can influence the behavior of a large set of loads. So very similar to the kind of the underfrequency load shed, or just seeing if the load can help stabilize the grid, but doing it in a lot more directed and maybe some type of oversight where you'll know that there's a big event coming up at 6 p.m. so you can send out an incentive signal to try and get people to scale back their demand prior to that event. That way the system remains stable and nobody notices the lights going out. Volver Optimization. So this is a project we did with the American Electric Power Company. They were evaluating a commercially available Volver optimization scheme, and they wanted to see what kind of benefits they would get from it. GridLABD, we took their feeders, modeled it in there, and did some annual analysis to see what kind of energy savings and what kind of peak reduction they would get by deploying this technology. This project was very nice. It was fairly early in the GridLABD development realm, where we took the real-world utility models, did the annual analysis, and then after they deployed the system, our results nearly perfect, well, perfect in the kind of annual uncertainty realm, matched the results of the actual CVR or Volver optimization deployment, showing kind of like a 3% energy reduction or the peak reduction at certain times in the year. So that was a very nice validation of GridLABD. It also basically allowed American Electric Power to turn around and apply this to other feeders in their power system and evaluate where this technology might be useful and what kind of benefits they could see. This also led to a follow-on project with another branch of AEP down in Oklahoma, where they were deploying a different system, but we actually came up with a method of testing the impacts of Volver optimization before the system is deployed. So doing some simple changes on kind of standard distribution equipment, evaluating that, and then seeing, do you even want to look at deploying Volver optimization, all before you've actually done any capital expenses or lined up a vendor, just to see if the feeder itself is conducive to that type of operation. And that method was basically tested and validated inside GridLABD, and then we went out to the field and tested it and saw the results matched our expectations, and that's currently in the process of being patented. The example I went over earlier, or kind of mentioned, is the solar integration and mitigation strategies. This leveraged a lot of different inputs. The first one was improved solar and inverter models that were validated as a partnership with NREL. They have a lot more kind of history and expertise in the inverter and photovoltaic realm. So we coordinated with them to get those accurate models that are used in like the PV watts or the solar advisor model integrated into GridLABD. So as utilities or end users were doing kind of annual studies to evaluate the impacts of photovoltaic on their system, or if it would make sense to deploy, that we were using models that made sense and accurately reflected what a real photovoltaic would produce. These models were integrated into GridLABD and eventually used in a project with Grid Unity. Once again, they were Cato Energy at the time, and Southern California Edison. And the idea was to basically provide a front end where either a utility or an end user could indicate where they wanted to deploy photovoltaics, and then relatively quickly evaluate what kind of impacts that would have on the system. So it would run the simulations inside GridLABD underneath everything, and then provide some results back and say, did this, overload the voltage at certain points on your system, or are your transformers overloaded? And then allow the utility or the user to evaluate ways of mitigating that. Maybe you need to upgrade your voltage regulators. Maybe you need to reconductor a line. Maybe just reconnecting the solar to a different portion of the feeder would actually mitigate that, and then the customer is happy and the utility is happy. This was all developed under some funding from the California Solar Initiative, with some funding also contributed by the Department of Energy Office of Electricity. GridUnity developed the front end, which you can see down here in the lower right-hand corner. Very nice graphical user interface. When I get to the GridLABD demo here in a little bit, you'll see why that's a nice change of pace. This is a commercial product. It's basically a consulting type service that GridUnity sells and provides. However, a lot of the development that went into that in terms of how to evaluate the feeders and some of the interfaces is in the GridLABD open source, so it's available for others to use or to leverage for their applications. And then kind of some more recent research. As I mentioned earlier, we've been looking at kind of microgrids and reconfiguration for resilience and reliability. So if there's any type of natural disaster, can you leverage existing assets on your system? So if you have any distributed generation, can you use that to power critical loads like the nearby hospital? Or in a project we had with Washington State University, could they use their on-campus diesel generators to actually provide power to the City Hall in a natural disaster? And the reason why City Hall is included is because that was actually their disaster relief center. So if you can get power to somewhere that may not necessarily have a backup generator, or maybe it has a limited fuel source, to extend kind of the runtime. That way, if it's a truly major disaster, the lights don't go out after an hour when your backup fuel source runs out. And GridLABD is basically used to evaluate a lot of kind of the faster, more transient effects associated with operating a microgrid. Like if you switch it, what kind of issues are there on the system? What kind of secondary concerns do you have when you're doing it as a microgrid as opposed to a bulk connected system? So as a quick demonstration, I'm going to show you kind of what GridLABD looks like, what a typical model file looks like. This is a very simple demonstration. This is just taking one of those prototypical feeders I mentioned earlier and adding in 3% of the feeder rating in photovoltaics for January 1st, 2009. So not exactly the best time of year for solar, especially if you're in the Northern Hemisphere. But mostly it was to just kind of show you how GridLABD works, what the file looks like, and once again highlight kind of the time series and kind of time evolution behavior. Even something like photovoltaic, you can see that both simulations start out exactly the same, but once the sun comes up and you're getting some of that generation on the system, the power, of course, goes down when solar is included because the photovoltaics are providing some of it. However, when the sun has gone down, you see the curves do not match anymore. And that's because during the course of the day, you've changed characteristics of the feeder and your load is influenced by that. Maybe your heater is heating a little bit more at certain times of the day, or maybe it's heating a little bit less just based off the grid conditions. And as that goes throughout the course of a year, you may see more and more differences, or you might see some type of secondary effect at 3 o'clock in the morning. And it's not as important for this photovoltaic study, but for a lot of your demand response, that can be very important when you're looking at kind of doing peak reduction, but you end up keep shifting your peak to like 3 o'clock in the morning, where you're expecting your transformers to cool down and provide some kind of mechanical relief to them, but maybe you're not having that anymore, and it actually shortens the life of them. So the quick demonstration, this is why I was highlighting the GUI developed by GridUnity. GridLABD is a console application. You basically type it into the command line and run it. You'll get the outputs. You see there's warnings for this particular file because the efficiency was unspecified and the PV was oversized for the inverter. And then just showing some warnings, putting the output, drops down here, doesn't look very exciting. The actual GLM file is very much kind of like, if you're familiar with programming, it's an object-oriented style. So you define kind of individual objects and give them some characteristics. This is what's describing the overall distribution system. So this is basically an electrical connection point, and then there's some properties of the house. These are populated by those scripts I mentioned earlier, just to give you a realistic and representative set to conduct your analysis on. And As mentioned, it's a console app, so when you run it, basically what your output is, once it runs here, is a bunch of column-separated variable files, which is not the most useful thing to use, but it's a raw data format. So that's where a lot of the other projects have either built a GUI that goes over it, or they've turned around and done ways of extracting these data and simplifying the results so users can get them in a easier and kind of more meaningful manner. So GridLABD is powerful, but it does have a learning curve, and it's not the most user-friendly thing, just to be aware of. Just some current research that's going on with GridLABD. All of these are basically under the Department of Energy. Flexibility is a resiliency resource. I believe this project is actually being talked about in your next webinar. This is a project with Duke Energy and some of the universities and national labs looking at how to use both utility and non-utility owned distributed energy resources for resiliency. So using the OpenFMB harness, how can you control basically non-utility photovoltaics and resources versus utility-owned? Microgrids is a resiliency resource. I've touched on that. How can you use kind of existing assets in a disaster scenario? That leads very closely into another project on networked microgrids. So if you have multiple backup generators in an area, can you connect them together maybe for additional runtime or additional resiliency? The advanced distribution management system, kind of new ways of operating the distribution system and putting everything into a common format. If you recall one of my earlier slides, I talked about having to transition things into the GLM format. This is using the common information model to try and simplify that and get everybody on a common platform and a common basis. That way sharing models with your neighbor or other utilities is a lot easier. And in the transactive energy simulation platform, this is just improving some of the models and looking at different ways of evaluating or simulating transactive energy. So if you're using a price-based signal or some type of incentive signal to get your loads to behave in a certain fashion. And I wanted to just highlight the Helix project. This is actually tying into GridLABD. It's another Department of Energy project. This is a co-simulation platform, and what that means is you can take a lot of different simulators from different domains, so things like distribution systems, building energy management systems, if you wanted to do transportation networks or communication, and allows them all to talk together so you can get very complex, very high fidelity models and get a lot of behaviors that you ordinarily wouldn't see with just a single simulator. And this is another openly available project. GridLABD is just one of the many simulators within it. There are plans to do a lot more. And with that, that's the end of the presentation. Here are some additional resources if you want to learn more about GridLABD. The first page is kind of the first link is our just kind of generic resource page. Gives you a little bit more information and gives you links to some demonstrations. The actual source code is up on GitHub if you're interested in downloading it and looking at it or contributing to it. And then there is the wiki up on ShoutWiki. I will caveat that the wiki isn't always the most up-to-date, so some of the pages might not reflect the most recent capabilities inside GridLABD. And with that, I think we move on to questions now.
Great, thanks so much, Frank. That is amazing in the number of capabilities and sort of use cases that can be applied here. Along those lines, one question is, suppose you're a utility and you want to look at dynamic pricing, for example. You mentioned that it's not the most user-friendly interface. Is there sort of technical assistance available to help you do that kind of modeling and that simulation?
There is. The kind of landing page I had at the end of the slides, if you go to that, there's actually a link to some discussion forums where you can post the questions. Utility partners especially, we're very open to kind of, if you need to contact us directly, providing some assistance there just to help you get up and running with GridLABD. Or one of the other options we've done from time to time is if a utility is evaluating GridLABD, we can actually do an on-site visit and do like a little on-the-job training or just kind of a quick course on how to use it, especially focused towards whatever capabilities they're looking at. Barring that, if it does need to be something more complicated, we do have the ability to, through the Department of Energy, do either what's known as a Cooperative Research and Development Agreement, a CRADA, or some type of, it's almost like a commercial contract where the Department of Energy provides assistance to deploying this technology and getting the utility up to speed with it so they can evaluate it on their system. But the forums and kind of direct email are the first approach to that. And then if it gets to be more involved, there are kind of more contracting oriented approaches that we can explore to provide additional assistance if needed.
Great, thanks. Someone asks, what language is GridLABD written in?
GridLABD right now is written in kind of a mix of C and C++. We actually have a project that's working to fix that and make it all C++, but it is written in that primarily so it can be compiled and used on many different platforms. So we support Windows, Mac OS, and Linux.
Great, thanks. And I mentioned this question might be coming, and you may not be as familiar with sort of the GridPeak tool and its capabilities, but someone asked what are sort of the overlaps and complementaries between GridLABD and GridPeak?
Well, there's a lot of overlap because what GridPeak is presenting, some of that analysis is actually done in GridLABD under the hood. So it's very similar to the Grid Unity Southern California Edison or the Open Modeling Framework in that GridLABD is the analytical engine underneath those, and then like GridPeak is providing kind of the nice, more user-friendly front end and some of the additional analysis of the output to kind of put it in a format that a non-engineer can read and understand.
Great, thanks. I wonder, you mentioned sort of where some of the underlying data comes from, and you talked about how you could input data. I wonder if you could just talk a little bit more about some of the data sourcing. I know, you talked about some of the different test models that are already embedded and you can use as a possibility, but how would you actually use your own data?
So using your own data, the big thing that you typically run into is whether it exists and what format it is in. As mentioned on kind of one of the earlier slides, we do have a lot of conversion scripts, or the programs already have the capability to take a lot of the electrical model information and export that into a format that GridLABD can recognize. Where it really gets complicated is when you start getting into some of the kind of end use and device level parameters. So things like, what does a typical house look like? What kind of appliances are in there? If you have that information via like a customer survey, a lot of the parameters in our population script are pretty straightforward and easy to adjust to whatever information you got out of the survey. So if you know how much insulation or what type of construction a house might be, it's a pretty easy value to change in a population script. And then when you generate it for those underlying feeders or your feeder, it'll represent your system. Now, if you wanted to go into excruciating detail and get explicit information on like every single end user and every single home or commercial entity inside your utility, you could enter all of that and kind of do the conversion from whatever format it's in into the GridLABD format. A lot of people, one, don't have that information, or two, don't really want to use it for personal identifiable information reasons. If any of that is not available, where we typically get a lot of our kind of end use information is the EIA. I think it's the Energy Information Administration. It's a government-run kind of data repository. They have a lot of information on typical home construction, typical fuel consumption, appliance use, things like that up on their website. The other option is sometimes you can use complementary software. Like if folks are familiar with Energy Plus, it's a very detailed kind of building energy simulator. You can use that to extract information and then turn around and use that to populate the GridLABD model. But there are conversion scripts. If it's in kind of a common format, it's just a lot of times that information is either not available, or one of the other examples we've run into with utilities especially is it's tribal knowledge. It's not actually written down anywhere, but go ask Fred, who was a lineman 30 years ago, and he'll tell you exactly what's there.
Great, thanks, Frank. Here's a question. How divergent are the SLAC, SLAC, and PNNL branches of GridLABD? Is there any effort to unify these two versions of the code?
That's a loaded question. They're based off of the same code. They have diverged a little bit just because there's different capabilities going on. They theoretically should be 100% mergeable, and there are some efforts going on between PNNL and SLAC to get them all back up onto the common repository, or at least get a mostly convergent source code up there. I'm not directly involved with that effort, so I don't know kind of the details of how quickly that's supposed to happen. A lot of the underlying methods and the underlying capabilities are the same. Things like some of the microgrid analysis is being done more at the PNNL side, some of the transactive stuff, and then some of the kind of more interfacing and high performance computing aspects are being done at SLAC. So some of those capabilities have diverged a bit. We should be able to merge them into a common kind of code base, but I'm not directly involved in that effort, so I don't know if there's any additional challenges or if there's any kind of organizational challenges. To my knowledge, they're both still open source, which is at least a benefit, but they have diverged a little bit, and it can make it difficult if you want to try and figure out which one you should use. I highly advocate using the PNNL version because ours is the best, but I'm a little biased.
Great. Question about whether the tool can illustrate line loss. Is that a modeling capability?
Yes. It can, if you have the right information, you can explicitly extract the line loss from the system, either as kind of the power values at a specific snapshot in time, or accumulate it and get an energy. What it depends on is you having the accurate impedances for your system. If you don't have that information or the accurate kind of line layout, you can still use kind of placeholder values and get some information out, but it may not be as accurate. But GridLABD does capture that information and does provide it to the user. It's not necessarily in a straightforward, this is the line loss object, I'll just put this in my file and get the information out. It's a characteristic of all of the kind of lines in the system, and you have to collect it or analyze it externally. But the information is available.
Great, thanks, Frank. Maybe we'll do, I know we're getting close to the hour mark here, so maybe we'll do one more question, and then we'll close out. Last question: have you done a demonstration of EV charging and renewable solar with storage, and that its impact on the distribution grid? Is that a model you've run?
It is a model we've run. I haven't personally ran any of those recently. We have a project that's looking at it and kind of its impacts on the larger scale bulk power system right now, and that's an ongoing project. We did some research, it's probably about 5 or 6 years ago now, myself and Michael Kittnermeyer, another researcher here at the Pacific Northwest National Lab, looking at electric vehicles and how they could be either used as storage or integrated with storage, as well as photovoltaics, and what kind of impacts that would have on the distribution system. We extended that a little bit, mostly on the storage and photovoltaic side, to some work we were doing with HECO and MECO, the Hawaiian Electric Cooperative and the Maui Electric Cooperative. Those results are in reports that are openly available either on the PNNL website or on osti.gov, which is just the records repository. I know there has been some more recent work. I just haven't directly done it, aside from the current project we're doing, where we're looking at more of what are like electric vehicle impacts on the bulk transmission grid. But we're using GridLABD to get kind of a baseline of that. But the analysis has been done. It's just I'm not familiar with any recent ones that have been done in like the last few years.
Great, thank you, Frank. Well, and I want to thank you for the overall introduction to GridLABD. It does look incredibly powerful, and like it has a lot of potential capabilities. I have a feeling you may be getting some follow-ups, both visits to the links and maybe otherwise too. But before closing out, I just want to give you an opportunity. Do you have anything else you want to emphasize before we close out?
No, I mean, you covered it right there. GridLABD does have a lot of capabilities. There's a lot of functionality that's been built into it over the years, especially evaluating some of these more complicated kind of smart grid or distribution technologies. The downside of that is it has been developed primarily as a research tool, so it is a little complicated to use. There is a bit of a learning curve, but if you're willing to put in the time and effort on it, you can get some very, very good results, and it can actually save you a lot of time and money in the long run.
Great. Well, thanks again, Frank, and thanks to our audience for tuning in. Before signing off and closing out, I do want to tell you about another upcoming webinar, one we have next week on March 28th. That's next Thursday from 1 to 2. We're doing another webinar featuring PNNL modeling tool. That webinar will be on enabling high penetrations of distributed solar through optimization of sub-transmission voltage regulation. And yeah, hope you can tune in for that. Okay, I'll turn it back over to Mari for a closeout.
Great, thanks everyone for attending the webinar today. We'll get it recorded and out to everyone. And just a reminder that you can check out the upcoming webinar on March 28th. Thanks for participating.